This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Chapter 1 of our series, The Fabric of the Cosmos. In this episode titled, What is Spacetime?, we're going to unravel the concept of spacetime as a four-dimensional continuum and explore how it shapes our understanding of the universe. So let's dive in. Time runs slower on your head than at your feet. Right now, your body is quietly stretching time by a tiny amount. On a jet, your watch disagrees with the clock at home. In this episode, we'll follow those tiny disagreements to their strange source, the fabric of reality itself. Einstein's radical move was to stop asking, "Where is this event?" and start asking, "When and where is this event?" together. Every firework you see, every text your phone sends, every heartbeat in your chest isn't just happening out there in space or at some moment in time. It's a single point in space-time with 4 coordinates, 3 for position, 1 for time. Change any one of them, and you're talking about a different event. Physicists track these events the way a delivery app tracks a package, not just which city it's in, but exactly which step of the route it's on. Space-time is that universal tracking system for reality. Crucially, its structure isn't fixed. Mass and energy continuously tweak the routing rules, so two observers can disagree about distances, durations, and even the order of events, yet still both be right within spacetime's shared geometry. To see why this four-dimensional view matters, leave thought experiments and look at your phone. When GPS tells you where you are, satellites aren't just pinging distances, they're relying on relativity-aware clocks whose readings only make sense inside spacetime's combined map of when plus where. Miss that, and your location drifts by kilometers. Physicists push this further with particle colliders, smashing protons together, then reconstructing entire interaction histories from fragments, like crime scene analysts working in 4D. In both cases, the calculations only close if space and time are treated as a single, structured stage. Physicists make this 4D picture concrete with something called a world line. Take a single object, say, you sitting in a chair. In ordinary space, you're just there. In space-time, you trace a continuous line. Each point on that line marks where you are at a particular moment. Start walking, and your world line tilts. Board a plane, and it bends in a new direction through space-time. An entire life becomes a long, squiggly thread. Now zoom out. The universe is a tangled bundle of such threads. Earth looping around the sun, photons streaming from screens, satellites arcing overhead. Space-time isn't just a blank grid. It's the pattern formed by all these intertwined world lines, plus the rules that say which shapes are allowed. Some shapes are forbidden because they'd require breaking cosmic speed limits. Nothing with mass gets a world line that tilts so far it outruns light. That light speed limit does more than cap how fast rockets can go. It builds a causal structure into reality. Which events can influence which others? Draw a flash of light as a burst in spacetime, and it spreads out as a cone. Anything inside the cone can be reached by a signal moving at or below light speed. Anything outside is forever out of causal reach. Your present moment is surrounded by a vast, can't get there from here, yet, region. Curvature complicates this picture in a specific way. It changes which straightest possible paths, geodesics, world lines can take. Left unchecked, your natural motion is to follow these geodesics. Stand on Earth and you're actually being pushed away from your preferred path by the ground. In orbit, a satellite is left to glide along one of these curves, which is why it falls around the planet instead of crashing into it. This same geometry carries ripples. When massive objects like black holes collide, they disturb the surrounding structure, launching waves that stretch and squeeze distances as they pass. Detectors like LIGO don't watch objects get tugged by a mysterious force. They watch space-time itself flex, ever so slightly, as a wave sweeps through. A good way to feel space-time strangeness is to look at systems that only make sense in 4D. Start with your calendar and maps. A concert ticket isn't just row 12, seat 8. It's meaningless without a date and start time. Airlines quietly exploit this. Two planes can occupy the same place at different times without risk, but scheduling errors that overlap them in time become disasters. Stock markets do something similar. A trade's value depends on price and when it executes. Milliseconds matter for high-frequency algorithms. Rearranging the order of otherwise identical trades can change profits, just as reordering events in space-time can change who can affect what. In computing, distributed databases must agree not just on data, but on a shared notion of order, using protocols like logical clocks to mimic a consistent causal structure. Physicists effectively do this for the universe, reconstructing which collisions could influence which detectors so their models don't allow trades that clear before they're placed. Einstein's equations hint that space-time might be more like software than hardware. Update the code and planets, light, even clocks behave differently. Future detectors could treat black hole collisions as system logs, reconstructing how the program evolves. Your challenge this week: when you read tech news, mentally tag stories as better clocks, better sensors, or better models, and ask how each might sharpen our ability to debug the universe's source code. The deeper we probe, the less space-time looks like a silent backdrop and more like an active participant in every process, from brain signals to GPS to particle collisions. It may even have a quantum grain, like pixels on a screen, that only reveals itself at extreme energies. For now, we're reverse engineering its rules from the rare glitches we can measure. Before next week, ask yourself, when I picture space-time right now, what does it actually look like in my mind? Am I imagining a stretchy fabric, a web of events, or something else? And where does that picture start to break down? Then, think about a simple everyday event, like dropping your keys or watching a plane fly overhead, and ask, if this is really happening in 4 dimensions, how would I describe it as a path through space-time instead of just over time? Finally, as you move through your day, pause once or twice and wonder, if gravity is really the curvature of space-time around me, what here, Earth's mass, my own motion, the objects on my desk, would be bending that fabric? And how does that change the way I intuitively think about what gravity is? This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!